away some cards. So I have two $50 and one $100 gift card to Red Feather Bitter Creek Ale House.
Y'all can hear me, and I'll trust that Damon will give me a sound check on the web if there's a problem. So thanks for coming. This is the last of the 4 sessions this fall, and we did keep things a little closer to home this fall with our presenters, and it's been several years since I've done a fall series lecture, so I'm excited to be here. Ken set me up and said that I had to deliver a new lecture that nobody's ever seen before, otherwise no one's going to show. And so I'm doing my best, but I can't promise that you've never seen at least one of these slides before. But I do think that the story has evolved a bit, and as we continue to spend time with these facilities, new stories come to light. So even if you think you've seen a slide before, you should listen because maybe some stories have changed. And I can promise that all of you will see some new slides tonight for sure. So topic is about holistic lighting. I've been fortunate enough to collaborate with Chris Meek on 2 books now. Ken handed one out to everybody, and there's the pre-release copy of one. And I'm going to pick my favorite pieces from those 2 books, as well as some kind of more recent research that we're working on with our architecture and mechanical engineering students. There's a definite theme with regard to daylighting, integrated electric lighting, and simulation and metrics that are evolving to try to understand lighting, lighting sufficiency, lighting quality. So that's the overall nature of the talk tonight. Please feel free to interrupt. We do have a microphone for handing around for questions. And I'm happy to entertain questions as we go. So I'll, if you guys ask questions, you'll be keeping Ken busy popping up and down. So with that, I'm going to jump in. We are funded to be here and delivering this lecture thanks to Idaho Power, so it's only appropriate that we start with energy efficiency. One of the things that I think you'll hear tonight is that daylighting is certainly part of an energy efficient building, but it is much more than. It's part of a sort of more holistic approach to sustainable design as well. And I think it's important to understand that balance between visual comfort, human perception of comfort, and the notions of productivity, as well as the notion of energy efficiency when we're talking about daylighting design. And it's also important to note that you can prioritize a daylighting design solution to be more about energy efficiency, or you can design a daylighting design to be more about creating excellent places for people to live and work. And of course, we hope it does both. But it's possible to think about optimizing for either of those scenarios and be willing to give up a little bit on one of the other scenarios. So this is 2003 CBEX data. This is kind of a historic view of what the average building looked like in 2003. And I just want to draw the attention to the giant red box that shows that lighting represents in the neighborhood of 20% of our electrical end uses in buildings. So it is low-hanging fruit. But we all know that in the last decade, with going from T12 lamps to, in 15 years, maybe T12 lamps to T8 to T5, and now to more and more compact fluorescents and more LEDs. Perhaps it's even safe to say fewer compact fluorescents now with the emergence of LEDs, that, surely lighting is no longer the big low-hanging fruit from an energy efficiency standpoint, right? We have all these technologies that have eroded the potential to save in this lighting bucket, except for when you think of the most aggressive energy efficient buildings. All of a sudden, that concept, and there's some truth to what I was saying, but all of a sudden that sort of dissipates, and we realize that once again, lighting is one of the biggest pieces of the pie. This is the chart you may have seen before from PAE on the bullet building. Energy by end use, and I just love this chart because of all the diversity and the detail that they put into it. But the point I'm trying to make here is we've gotten extremely efficient in our HVAC, heating, lighting, cooling, or cooling, ventilating systems, and even with lighting power density allotment in this building of just 0.4 watts per square foot, which is something in the neighborhood of 50% what's allowable by code, or even just 35 to 40% what's allowable by code. Even with just 0.4 watts per square foot, it's still the biggest piece of the energy pie. So daylighting by extension is going to continue to be important even into the net zero energy building genre or era. A lot of words on the screen. I don't have many slides like this, I apologize, but this is a really quick way to do a dump of what all the studies say, all the research findings say about lighting energy savings associated with daylight harvesting. That is dimming your electric light or switching them off based upon daylighting as it's available in your space. And they're grouped into two categories. Well, the top one just says, electric energy and lighting is still a very big energy resource within our country, something in the neighborhood of total 19% of all of electric use in buildings is for lighting, or all electric use in the U.S. is for lighting buildings. And then there's two chunks of results. Laboratory studies, I think PhDs on ladders, really carefully commissioning the building system, the lighting controls, so that they work perfectly with regard to the daylight available. And then the other group is the real world, the field studies. And one of the things that you'll notice if you look at the numbers is that we're not seeing the same realized savings in field studies from daylight harvesting as we did in laboratory studies. Obviously, there are fewer controls, and people do their thing, and modify lights and modify blinds and snip sensors if they don't like the way that the lighting is being controlled in response to daylight, or put tape over the photocells, etc. And so we're seeing something in the neighborhood of a 50% realized savings ratio. And that's up from just 25%. So 5 or about 10 years ago, there was a study of about 100 side-lit buildings, and half of the buildings saved no energy from daylight harvesting, and the other half saved half of what they thought they should have, for a total 25% realized savings. Whereas top lighting performed better, but nonetheless we're improving, and I think that's an interesting and important trend. Brad did a study in 2010. There are 2 or 3 more studies recently that show we're approaching double that performance, or about 50% realized savings ratio. And so I think that suggests we're making great progress as an industry. Priorities on commissioning, priorities on human behavior and educating users about the intention of the lighting controls. But it also says, obviously, that there's a long way to go in terms of improving the performance and getting all of the savings that we think we're going to get out of our daylight harvesting lighting control system. This is what it looks like maybe in a real building, and some of you have seen this one before. This is Terry Thomas. Installed lighting power density of 0.6 watts per square foot. See, that's when you take all the load, all the lighting energy used, and you divide it on a per square foot basis, so connected load. Think power draw here, 0.6 watts per square foot. What's interesting, because of the daylight harvesting and a pretty simple control solution where they're not getting too fancy or too tricky with their lighting controls, their measured or effective lighting power density is in the 0.26 range. So that's a metric. Again, I told you I'd talk about metrics. This is one that we use a lot, but it's a little bit of a finer look at it when you start thinking about effective lighting power density. That is giving some credit, perhaps in a code or whatnot, to the notion of daylight harvesting. So another big important piece about, whenever we talk about energy with regard to daylight, we think, well, the more windows we add, the more opportunity there is for heat gain and heat loss. And so really the most energy efficient solution would be no windows at all. And what this chart shows you is that's not the case. The orange graph shows you Boise, Idaho, and on the bottom axis we have, am I good to walk around a little bit, Damon? I forgot. Okay. On the bottom axis we have window to wall ratio. And remember, a prescriptive code for a commercial office building would say you're allowed 40% glazing. And if you want more glazing than that, you're going to have to prove it through some sort of performance-based code compliance protocol. And then on the vertical axis, we have total building energy use. Now, we're looking, anytime we do a chart like this, you have to know the assumptions. So the assumptions in this chart is the south-facing zone. Another big assumption is we're just assuming that the blinds are going to be open. Which is not always the case. That's a caveat to hold on to. And then what we're seeing here is, indeed, as we think, as you add more glass, you increase energy consumption. This is energy use index, so it's going from about 52 at no windows up to 63 or so EUI, total KBTU per square foot year, as you add more and more glass, up to 70% glass. But a couple interesting things come out of this, and that look at daylight harvesting, well, now we start to see a sweet spot. And in fact, the most energy efficient building is not the building with no glass. And then a little bit more of a fine-tooth look at that, still, when you add different types of glass, you can see that that performance can be maintained shorter or longer based upon, double pane, low E, solar heat gain coefficient, visible light transmission, triple pane, better U values, et cetera, et cetera. We see that we can maintain that performance longer, all the way out to the point where you can get to 70% glass with a good triple pane piece of glass, or effective triple pane. There are double pane units that have performance characteristics similar to triple pane. You can get all the way out to 70% window to wall ratio and still be using less energy than doing no windows at all. Now that's another big caveat, is that the daylight harvesting system is indeed working, and you're getting 100% of the realized savings, not 50 or 25%. So I think this is nice because it gives us as designers a lot of freedom. Code continues, and I've got Ken Baker in the room, one of the U.S. foremost thinkers in energy code and leaders in that area. But the downside to code sometimes is that we can get painted in a box, and we're limited in our in what we can do from a design standpoint. And what's really encouraging here is that code does not have to mean you don't do well daylit buildings. You may have to go through a little bit more effort, do a performance-based approach, etc. So I just wanted to start off with that kind of an energy picture to set the stage for the evening. Then I want to move on and talk a little bit about the two books that I promised to hit some high points on. And if I'm going to talk about these books, I need to acknowledge Chris. He's co-author on both of them. And in fact, really, most of the work that I've done in the daylighting area has benefited reciprocally, I think, with Chris Meek at University of Washington. So I'd like to give him a lot of credit. The first book here is really more of a monograph of daylighting in the Pacific Northwest. It's projects that we had a touch in at one level, some maybe a deeper touch, some a little bit lighter touch. And one of the things that we wanted to do is try to document these really beautiful daylit buildings to kind of, so much about daylighting is about the energy side of the problem. And I think it's important to remember why we're designing these buildings in the first place, is create elegant, beautiful, functional places for people to live and work. And I'm going to stand on my soapbox just a little bit about architectural photography and say that, most architectural photography is captured at the magic hour. Sunrise or sunset buildings that are illuminated inside, but we have enough light on the outside to see the exterior, increases drama, creates for really elegant, warm and cool color contrast architectural photography. But in the book, that was not what we wanted to do. Instead, we tried to turn this convention inside out. We wanted to show interior spaces under the patterns of daylight present during the more typical times in the life of the building. We took a thumbnail approach to the exterior photography, as you can see in the bottom right, and instead celebrated these interior, expansive, well-daylit scenes, always photographed with the electric lights off, unless the electric lighting was a very intentional part of the overall lighting design. And sometimes it is, and sometimes it isn't, and that's one of the themes that I want to pull through this talk tonight as well. So this is the J. Chris Gallery. You might look at these images and say, yes, this is just one moment in time. How does this perform in the late afternoon in December? We recognize this challenge, and we agree with its premise in this book. We're chasing light with words and photographs. The truth is in first-hand experience of the architecture through time. Our hope is that this work encourages readers or participants to reassess their functional potential of daylight in buildings and embrace the dynamic qualities that make daylight so compelling. Our intention is to inspire designers and building users alike to raise the level of their expectations about what a daylit space is, and to provide instruction on how to improve daylight design in buildings through an examination of successful examples. We also vow to reveal the lessons learned, both the successes and the failures of these projects for the sake of success or progress. So I wanted to start off with one really important lesson if you're going to really get serious about daylighting design in buildings, and that is to set design criteria and test design decisions. And this gets a little bit of some process tools that I think architects and engineers can bring to their practice and use to achieve this, both setting design criteria and testing design decisions. use the Novelty Hill Winery north of Seattle as a case study to illustrate this point. Just kind of give you a sense of the exterior architecture here. South-facing facade we see there with an array of trees. Starts to, especially as these trees have matured over the years, starts to help the user adapt their eye down to the darker interior environments that we'll find in even a very well daylit building. The contrast from going to a sunny exterior to a darker interior can always be jarring, and you can see we wanted to try to find ways to dim that down through an exterior canopy, which I'll show in a minute. But one of the things I wanted to talk about on this project is the notion that a building like this, a small winery, still has a pretty wide diversity of space types. And that diversity in space types gives us the opportunity to think a little more critically about our daylighting goals. It doesn't have to be a one-size, 30-foot candles, horizontal, on the floor is the goal every space. Some spaces want more drama. Some spaces want more control. Some spaces want to be dim. Some spaces want to provide functional illumination for 24/7 type processing and work. So kind of going through that process, you can imagine, here for a winery, we have a function room, a tasting room, different priorities there versus the barrel room, which wants to be dark, and the fermenting chamber, which is more about functional illumination. That sets up different expectations for daylighting in each of those spaces. The same would be true of a school building. Here, looking at core classrooms versus gyms and shops that maybe have more opportunity for top lighting, a theater that maybe wants to be dim or at least have the foreground of the theater dimmable so you can have AV presentations, gyms and shops and circulation areas that allow circulation areas that maybe allow for a little bit more dynamism within their spaces. So again, I think this concept carries beyond a winery, which is a little bit of a one-off. Not everyone gets the chance to design a winery all the time, but more and more often we'll have chances for schools and offices, and I think the concept can apply there. So back to the winery here is very much about layers of transparency, wanting to engage that indoor-outdoor experience. And one of the ways to do that is to create a bright enough indoor environment that as you move in, it's not jarring and dim and you have to wait for your eyes to adapt. And vice versa, when you're inside, that it's not so dim and dank inside that you can't see out well into the foreground. So an exterior translucent canopy here, and then washing these dark kind of natural form concrete walls with daylight and the skylights here. You can see just a little bit of a sharp shadow. Those are actually clear skylights, which we don't do all the time. And then here we have the electric lights on because it's very much about creating a center of focus, kind of bringing our eyes to those tasting tables. From a functional standpoint, it's also about punching some good quality light down onto the wine glasses so that you can have a sense of the color and clarity of the wine. And then if you look into the distance, you'll see another glass wall, which allows a peek into the fermenting, into the barrel storage room. One of the challenges with these bright interior spaces looking into a dark room, or even think of yourself on the street front on a sunny day looking into a relatively dark building, is you get a mirror effect. And so one of the ways to try to to correct for that was to bring just one row of skylights in to wash the barrels with light so that you have that sense of transparency into that tasting room. There's some functional things that help here too. It happens to be a chaseway for the forklift in and out. We wouldn't want lights flipping on, off all day long, even if they were on occupancy sensors. There's not enough daylight here to be dimming the whole room. So it provides some functional illumination for that forklift to go back and forth. Here you can see the contrast with the fermenting room, which is much more about providing enough foot candles around the room so that the people can measure and use their instruments and walk the scaffolds, etc., for the process in and of itself. So thinking through those spaces is important, the space types and the lighting criteria. And then, of course, once you've set criteria for a space, you want to take an iterative design approach towards analyzing that space. And there's a host of tools available, increasing all the time. You're seeing the overcast skybox and the Heliodon, which we still use, but more from a teaching standpoint, into some of the more the newer digital tools that are available and more functional, accessible to designers. At the bottom right, you'll see this is called a high dynamic range photograph, which allows you to take a real-world photo of a space and get pixel-by-pixel brightness values that you can use and calibrate to the renderings, the digital renderings like what you see up above. Here is just showing a kind of ISO contour line. Here is just more of a gradient scale, but you would be able to look at this information in a similar capacity. You know, and then a sense of calibration. You want to build yourself a sense of calibration for these tools. So this is the real-world Yesler Community Center versus the physical model that was used to test those design decisions early on in the process. And here another example. This one is Chartwell School by EHDD down in San Jose, California, and the image of the classroom, photograph of the classroom on the top left and the rendering on the bottom right. I will say the rendering on the bottom right wasn't a design tool. That was a post-construction kind of recreation. And, you know, I find myself wanting physical models and digital models on every project that give us different information. Most of the time we don't have that luxury. We're lucky to get one model, but here's an example of a College of Southern Idaho Tech building where we did have the chance to do both physical models and digital models. The nice thing about digital models is you can look at annual cloud files, whereas with physical models you have one point in time that you can look at the results. Nice thing about physical models is you can look at them with your real eye, and in digital models you have this sort of obscure screen and its screen brightness, etc., in between you and the data. So, you know, this just shows an example of how close you can get with some of the digital models. Photograph on the top, rendering on the bottom, and then the false color, which again is that pixel-by-pixel brightness value of the HDR photograph on the top and the radiance rendering on the bottom. So we can really be sure that we know how to define material characteristics and that we can use this for scientific purposes as well as qualitative analysis. All right, lesson 2. This one's a local one, and it sounds so simple. Put the daylight where you need it the most. It should go without saying, but it's critical to identify where daylight is most valuable. It really carries off to that first lesson where I talked about setting criteria. Same concept here. Thinking about where the daylight is most valuable and focusing our design intention to create highest success in these areas. It may be tempting to lavish attention on one-off signature elements such as entry lobbies or corridors, but the greatest challenge is designing fundamentally daylit buildings lies in the design innovation required to provide broad access to high-quality daylighting views within the spaces where building occupants spend most of their time. This is an architectural record photograph of Clackamas School. It's a great school. Bora architects, really excellent architects. But one of the things that I think it does, now you can save a lot of energy in hallways, but people don't spend as much time there. And you can handle a lot of the lighting savings with occupancy sensors, and probably, and not every building has the access to daylighting resources in your corridors as well as your classrooms. So, you know, this is not the case at Clackamas, but so often we'll see these beautiful daylit hallways in dark, dingy classrooms where the kids spend all day. And what I really like about McKibben Cooper's local Head Start building, if you haven't been here, it's worth the trip. It's 36th Street, just north of Chinden. Nice, beautiful little building, designed in 2000 and built in 2002. And what they did was they took that notion of those beautiful daylit lobby spaces and they stole that daylight resource and put it in the classrooms where the kids spend the most amount of their time. It's a traditional butterfly roof with an interior multi-purpose room, and this would be normally where the exterior envelope is, putting daylight into that multi-purpose room or think hallway, etc. And instead they extend that butterfly roof and put it in the back side of the classroom, which I think is just a really elegant move here, you can see. And that allows them to daylight the classroom, but they can also borrow a little bit of that daylight back into the multi-purpose room. See through these relights here. in these relights here. So, and then at the entryway, it bumps out and you get natural daylight from the exterior envelope through and into that space, and then here and here and here and all these lower windows are where the relight comes through. All right, one more lesson I think from this book happens to be lesson number 6, so I skipped a few. As architects and owners strive to create higher performing buildings, the role of occupant behavior becomes increasingly critical. Architects can design buildings with the potential for effective daylight performance, but realizing this performance expectations requires users to operate the building in the intended manner. This is particularly true with regards to window shades and blinds, and in fact this has sort of spawned a big research agenda within our lab more on the unfunded kind of academic research side of the coin right now. These shots are from Chris's friend, Craig Johnson. He's the building operator at the UC San Diego campus, and he has this habit of walking around and capturing photographs of these intentionally daylit buildings with lots of blinds drawn closed. And this is not doing anyone any benefit, right? The views are cut off, and we're getting the solar gain, and we're losing the heat out the envelope. And there's just an interesting study here about user behavior. It just so happens that people don't spend all of their time worrying about the blinds to make sure that your optimized daylight harvesting system gets all the energy savings expected. They have other things to do, as it turns out. And it's also interesting to see the effect of shading. Here on a south-facing wall, the blinds are sort of open behind those trees. The dappled light comes through, and it's not a big of a problem. On the north facade here, we just don't see as many blinds closed, not as much solar gain, not as much glare, etc. And occupants will find a way if you don't provide them blinds, perhaps not to the greatest aesthetic effect as desired by the architects. So we took this as a challenge, and we're trying to wrestle this problem to the ground. And one of the things that I think has emerged is the realization that from a daylighting modeling standpoint and from an energy modeling standpoint, we cannot just assume the blinds are going to be up all the time. And unfortunately, I would say until about 2 or 3 years ago, nearly everyone, and you pick the fanciest architectural or engineering firm doing, the high-performing zero-net energy buildings, I'll put them right in the same basket and say nobody is considering blinds in buildings. So the first question is, well, how much does it matter? And I'll just kind of start to unfold that a little bit for you. We are starting to make it a habit to put some sort of occupancy profile that we think is believable and a blind use profile that we think is believable into our energy modeling, because we're starting to see that it makes a difference. So an east-facing office, the graphic on the left shows you what we would expect to get from a daylight availability over the course of a day. So the bottom axis of that graph is the hours of the day here. And then this is available daylight at a point, I think it's sitting center in the cubicle here. And then this is what happens over the same day if the blinds were closed. And that red line is our control criteria. Let's say we're dimming our electric lights so that, if the daylight available is above this criteria, then we're going to be turning them off or dimming them. And if it's below that criteria, we're not going to be turning them off or not dimming them as much. So you can see big difference, right? We know it matters from a daylighting standpoint. This is what that looks like on a facade with current best practice rule set. This is over the course of a year, so whether the blind is open or closed is highlighted in blue, and whether it's half closed is here versus all the way is up the vertical, and then the months of the year at the bottom, 365 days a year. So this is a piece of software called Light Switch that is available, but only in the Radiance sort of scripting level interface. Most people aren't going to use that. And all of the red times are showing when the blinds are closed. So on an annual basis, we know this really matters. We feel like this rule set was a little simplistic, and so we did a literature review to find how many people have gone and take photographs of buildings and the blind positions, etc., and what are people doing with their manual blinds, and can we predict it? Is it because of privacy? Is it because of solar penetration? Is it because of glare? Is it based upon a certain total brightness on the facade? What are these proxies that we can use to estimate how a standard user will probably operate their blinds? And we came up with these two models, and I'll just very quickly explain them. One is based upon, is it sunny or cloudy? And if it's deemed to be sunny, how far in is the sun going? And the other one is based upon exterior vertical surface brightness, and if it gets above 20,000 lux, it starts closing blinds to the point where it reaches 100,000 lux, and then it won't open those blinds until the exterior brightness dims a little bit. And so another interesting finding is that the anecdotal information is everyone keeps their blind closed all the time, so forget why should we bother doing daylighting. Well, that's not what we found in the study. We found that about 5% of the people keep their blinds down and closed all the time. About 15% of the people keep their blinds down but rotated to keep sun penetration out. And about 20% of the people leave them open all the time. They're the sun seekers. We have the cave dwellers and sun seekers in our world. And then there's about 60% of the people who operate according to some of these models that I just described. And so our current research is trying to understand what are the energy implications of these different blind control models. And so I'll just show you, this was Chris Dyke's thesis, and Amir at our lab is now picking it up in his thesis. And what we found is there's up to a 28% total annual energy end use discrepancy based upon the blind pattern, whether the blinds are on the inside of the building, on the outside of the building, whether the daylight harvesting is working or not working. So this is really a daylight harvesting and blinds effect, up to a 28% swing. When you start looking at some of the minutia, the answers don't seem to be as detrimental. But you can see here is the baseline energy use, and you see the black is general equipment, which didn't change over the course of our study very much. A little bit on pumps regarding heating and cooling changes. This gray is the heating energy, this gray is the cooling energy, and then this is the lighting energy. So the big jump down here, EUI of 63 down to 51, if we assume the blinds are always open and the daylight harvesting is working perfectly, versus something like blinds down and always closed here, an EUI of 58. So 51 to 58 is a pretty substantial swing if we're that's the effect of the blinds, assuming daylight harvesting is working well. So my point here is that it matters enough to try to get right within modeling, and it could change the order of energy efficiency measures if we're doing something that's really trying to do a fine slice on the cooling, and the blinds were assumed to be open. Now the blinds are using some sort of manual operation schedule, and that may change the energy efficiency measure that you choose to apply to your cooling system. All right. Good chance for a pause there. Sometimes I get on a roll and don't let you get your hands up or get the voice out. Anyone have questions on that so far? I'll pick up a couple of these themes again. So, all right. Integrated daylighting and electric lighting. Has anyone seen me talk about this slide set already? Gunnar, I know you have, but anyone else? Russ? All right, that's only like 5% of the room, so I'm going to go for it. This is the old lab in Seattle. They have since moved into the Bullitt Building, our sister lab, if you will, the Integrated Design Lab in Seattle. And this is what it would look like as I was flying back and forth between Boise and Seattle trying to get my PhD done. I'd often land, I'd take off at 6 a.m., land at 6 a.m., I'd be to the office by 7 a.m. It took me as long to get from the airport to the office as it took me to get from Boise to Seattle, which is kind of funny. Because of the time shifts change, it was literally no time, right? But it was about an hour to get there, and then an hour to get from the airport to this setting, which was right around 7 a.m. in fall at the lab in Seattle. And I'd be the first one there, and it just didn't seem right to turn on all the electric lights in one fell swoop. And so I'd hit a couple of task lights, and maybe I'd turn those drum lights on down the hallway here. You can see these. And that made the whole space feel like it was on, made the whole space feel like it was open, sort of cast the shadows out of the corners. And that's how I would work until the building automation system came and turned on the overhead ambient lights. So back again from here to here, you can see the overhead ambient lights come on. You can see the exterior daylight starting to ramp up a little bit. We have these really tall windows with the blinds down but rotated open. And then as the day progressed, and I sort of note the little squiggle on the report cover here. That's one of those lamps here in this fixture reflecting, so you can see that it's on. And then here, as the daylight ramps up, those lights stay on, but they dim down. So they don't de-energize, but they ramp down to a minimal setting. And then eventually, depending on our set point and our time delay and our deadband, all these lighting control terms, depending on how we have those set, eventually that little report cover squiggle will go away, as you can see here. And the overhead ambient light will simply de-energize. We know that if we leave those overhead lights on, even at their minimal setting, we're going to be burning some in the neighborhood of 10 to 20% power. So it's really great if we can take that next step and turn them off. That's if it's a fluorescent lamp. But LED, of course, are better. What's really important is if you're going to take that step to go ahead and turn that light off, make sure that when it comes back on, it doesn't come back on at full and then ramp down, because that can be really jarring. And I think the notion that obviously we're visual creatures. 80% of our perception comes from our visual environment, and that can be jarring. It can be a sign that something's wrong with the lighting system. It doesn't seem like it should be doing that. It's disruptive. It makes you notice it. The lighting should maybe not be noticed, right? Or the fixtures, they should just do their thing. As the day progresses, we might need a little task lamp here and there. We've designed the overall lighting for this room to be pretty meager. The overhead ambient lighting is around 25, 30-foot candles. So if we want a little bit of a punch on our desk, we have occupant-controlled task lamps. Note that those decorative drum lights in the back are just staying on. Again, that gives us the sense that the space is open. Sometimes we need that visual cue. We walk into a room with no electric lights on, and we think, "Is anyone here? Are we open for business?" It also provides a little bit of visual focus to the space. In Seattle, we'll get this sunbreak in the afternoon. I always talk about the sky dome in Seattle like a skull cap, where you get the little sliver at the horizon in the late afternoon sun or early morning sun, where you can see the mountains and the sun on the horizon. And we like sun in Seattle, but if it's this, then we have a problem. And then we have glare, and then someone's going to take the time to go ahead and close that blind and hopefully open it again. We know that a good view is daylight's best friend, because if we have an elegant view to Elliott Bay, we'll take the time to open those blinds back up. Even non-daylighting geeks will take the time to open those blinds back up. And as we move into the afternoon, kind of a similar phenomenon as we saw in the morning. After hours, I'd fly home usually around 9, so I'd have to hit the road from the office around 7 to get to the airport on time to check in. And this is how it would be again in the afternoon before departing. And so what I like about this slide deck, that little series, is that it's totally achievable. And it suggests a story about lighting and daylighting integrated design that is more than just energy savings. There's certainly an energy story here, but I think there's a very achievable, finer level approach to the lighting system here. It's simply occupant-controlled task lamps, building automated system-controlled overhead ambient light with daylight harvesting, manual controlled blinds, some decorative drum lights that are meant to be on. We're going to let those burn, even if we could save the energy. It's part of the overall design intent to make this space feel like it's inhabited and give our eyes something to explain why there's all this light in the room. And it's really simple. It's everyday architecture. It's a nice office building. Yeah. Go ahead. It was a new building. It sat empty for several years. They were the first tenant, and they have since moved out. That's true. The lighting design was part of a tenant improvement fit-out. The daylighting was what it was when they came. It was a spec office building. So the question is, how can we achieve some of this for an existing occupied building? You know, I think historic buildings are great because they typically have some decent daylighting bones to them. So from the daylighting standpoint, at some level you're going to get what you get, except for you do have some retrofit potential. You know, there are certain technologies, and I know Solitude's in the room, that lend themselves better to daylighting retrofits. If you come to the Integrated Design Lab, you'll see 9 different skylights retrofitted into the roof, and I will tell you the truth about which ones maybe I wouldn't do again. For one, I wouldn't cut a 12-foot by 8-foot hole in a 75-year-old built-up roof. I won't do that again to put a real large skylight in, but I would absolutely cut smaller holes for you know, 4x4 skylights or tubular daylight devices. I think you can retrofit some daylighting into buildings. The other thing about it is there's the perimeter zone, and every building's got a perimeter zone with some access to daylight, and we can focus our daylighting lighting controls into the spaces where you have good daylight. And then beyond that, I think, is just sort of being willing to admit that there are some spaces in your building that aren't going to lend themselves well to daylight electric light integration. Some spaces that are really going to have to be electrically illuminated most of the time. And I think you can still provide occupant control. You can still provide some layering of light. And I think I'll kind of hit on a little bit of that here. Any other questions? Yeah.
It's kind of, I should have asked this probably right before I started this. I'm going to go back to that line work that you've been starting.
Mm-hmm.
And whether, this is maybe fine grained, but whether or not you've seen a difference or looked at the difference between the type of user and the type and or the type of line and the type of operation.
Right. Right. So the question is, with regards to the blind use patterns that we found in the literature, is there a difference for type of user, type of blind, and other variables that maybe start to explain how people use blinds? And there's a little bit. We've done some original research data collection, but we've yet to process it, where we want to look at the view quality, the view quantity, the privacy issues, whether it's on a ground floor or on an upper story, and then I think there's going to be some sort of profiling. I don't know exactly how we'll get to it, because it's really hard to collect data about individuals, about a survey, about why they're doing what they do. We haven't been able to accomplish that yet, but I think we'll probably come back to, okay, the buildings that we've looked at, you know, 5 or 10% of the people seem to leave their blinds alone, always open, 20% always closed, or whatever. So we're going to try to test those ideas a little bit. Gunnar?
When you did your thesis study, you saw a few things that had higher ranges of acceptability and luminance in certain groups, didn't you? I mean, it wasn't connected directly with what they did.
Right. So Gunnar's talking about one of my research studies on visual quality, visual comfort, and one of the big takeaways was that most people, something like 80% of the people, wanted sun in their space so long as it wasn't in their face. And that works great in private offices or sparsely occupied offices, but it's a little bit more of a challenge in open plan office. And so that would be another confounding variable that we'd like to try to understand is, are these open plan offices or private, because there's a sense of ownership over the blinds in a private office, whereas in an open plan, it's sort of this community control thing. Who owns the blind? The person by the window, or, you know, is it lowest common denominator? If it's glaring for one, we are shutting all the blinds, that kind of thing. Other questions or comments? All right, so this is kind of a fun series. This is one that I promise is new. I think it's even new for you, Gunnar. This is something we write about in this book, but I didn't, you know, the book doesn't lend itself to the sort of imagery here. There's a little bit of a screen. There is an image in the book, a few images, but this is going to be more fun, I think. So this is our office space with task lights at night. and this is with the incandescent par lamps washing the wall. Perhaps the spotlights were a poor choice there. They look a little ugly, and I'll admit when we had them in, they kind of felt a little ugly. Probably should have done a little bit more of a flood on that wall. The overhead ambient lights, but dimmed down. And then here, those floodlights ramped up. So here the floodlights are dimmed, or the spotlights, and here they're ramped up. And then here, the interior lights more on full. And what I like about this is, again, it kind of illustrates this story of layers of light and availability for occupants to engage with some, but maybe not others. So in our space, we have everything controllable manually. And that's just because we like to play with it. So we have task lamps we can turn on and off. We got wall washers that we can dim up and down. We have overhead ambient lights that we can dim up and down. This one is starting to look at, this one is sort of how we prefer to occupy that room in the evening, at least when I am there working alone. This is how I set it up. A little bit of wall wash to make the whole space feel like it's open. Again, get some of the darkness out of the corners. And then really just task lights for my desk. This is when we implemented the LED lighting. So here is incandescent wall wash and incandescent task lamp. And then here, sorry, it's a little lagged. And here is with LED task lamp and LED wall wash. The first thing you'll notice is the color temperature shift, right? Relatively warm. You measure color temperature in degrees Kelvin. So this might be 2,500 to 3,500 degrees Kelvin. And it's convoluted. But as the color temperature gets bluer, you will call it cooler. But it's actually a higher degree Kelvin. So this is more like 5,000 degree Kelvin lights. What's important to note is this is not just par lamps versus LEDs. This is color temperature. And you can specify color, cooler or warmer color temperature LEDs as well. It's also a nice lesson to say, wow, that, in my opinion, that has a dramatic effect on the perception of being in that room. This has, you hear warmer colors or sort of more residential, some of the big hotel chains fought CFLs for years and years because they couldn't get warm CFLs, and of course then eventually you could. Same thing happened with LED. Now you can get warmer LEDs. This has a little bit more of a sterile feel, but some would say it's a cleaner look. Not only cleaner because it's not these poorly positioned spotlights versus a more appropriate wall wash, but also cleaner because of the color temperature. And that's just another tool that we have as designers to create the perception of visual comfort or visual quality within our space. And then you start to see I think this is a little troubling. You can see the stark contrast between the 3,500 Kelvin fluorescent lamps and the 5,000 or 5,500 Kelvin wall wash. Thinking about this from a retrofit standpoint, this could be problematic. I almost think it works here because it's two separate surfaces, but you definitely wouldn't want to see two lamps swapped out with 5,000 Kelvin and 3,500 in the others, right? That would be hideous. It almost works here, but I still think it's a little troublesome. Well, there's one last thing here. This is at night, and then this is, of course, in the daylight. So this is just a little thought experiment that we're playing with. I'm not sure that it's far enough along to call it a resolved idea yet, but I think we're just trying to understand the perception, the psychological, and maybe to some extent physiological perception or physiological effects of these different color temperatures. This is with the par lamp wall wash under daylight, and this is with the LED wall wash. And obviously, that blends much better. Daylight during the middle of the day tends to be a much higher color temperatures. We always think about daylight as sunrise and sunset, those warm tones, but most of the time, daylight is extremely high color temperature. And so thinking about the light sources to balance the daylight, either to contrast with it or to blend with it, I think is another tool that we have. So that's where I wanted to come to with this little series. Hopefully this works. And hopefully I don't get too lost trying to navigate over to, there it is, view, full screen. This just we happened to catch this 1 minute clip where the daylight and the clouds were moving around pretty fantastically. And we had, from our daylight harvesting commissioning class, we had these new LED fixtures installed, which you can see there. But also they were set to the commissioning mode, which means they have instant response to the changing in the daylight. And as the clip moves on here, you'll see a little bit more. It's a little washed out on the projector versus on the computer screen. But you'll see the daylight ramping up and down as clouds move by, and you see the fixture responding. And I just want to point to why a deadband or time delay might be important, because you can, it starts to feel a little troublesome, but also the notion of color temperature. So it's a little harder to see on the screen, but if I kind of move through it, it's a little bit more pronounced. So this got me thinking about, could we take these new technologies with LED, which can do color shifting, and start to balance for this kind of shifting over the course of even a few minutes. One of the things I think was we want the automated lighting control to be less perceptible. If it draws attention to itself, I think it has greater risk of being overridden by frustrated occupants. And so there's this cool new LED technology that allows for color temperature shifting. We know about color changing LED. This is more sort of refined. And you can just see it here. This little diode, this little dial rotates, and it pushes the light through more or less of a glass emitter, and that shifts the color temperature, where you can get more yellow or more blue. And this is pretty seamless. You can do this manually on this particular fixture, but one could conceive that this could be done automated fashion and start to balance some of this, which occurred over the period of just a minute, and try to make the color temperature in that room balance out a little bit more, draw less attention to itself. Or you could decide it's a design tool and use it intentionally and draw more attention, right? As long as you're careful with it.
The Riverside Hotel actually has some of those color shifting already installed, and they go from a 2700 at dimming levels up to a full 4000 at full task lighting, which works really well for kind of keeping that warm look when you're trying to keep things cozy, but when you go full blast, it pumps them up to 4.
Okay,
so
cool.
If anybody wants to go take a look at some installed, I think they're made by Philips.
Nice.
They're a pretty amazing light. They look
Is
really
it
well.
the fluorescent where they have 2 different color temperature lamps switching, or is it LED?
It's an LED bulb.
Yeah, cool.
So they were pretty brand new when they got installed, but they're pretty neat.
Yeah, thank you. I'm always looking for new examples. So if you see things, trying to keep pushing this idea forward. So that'd be great to see. If you notice good case studies, send them my way. All right. So this is, again, another kind of transition point within the slide deck. So are there other questions before we move on to the last chunk of the presentation? So practice to research to hopefully back to practice. That's our goal, right, at the Integrated Design Lab or academia more broadly. So new tools for designers. This is Daylight Pattern Guide plus Energy. I'll hit the Daylight Pattern Guide really quickly. I know some of you have seen it. I don't think all of you have, so I at least want to show it. And what we're trying to do with this tool set, and this is a project I've worked on again with Chris Meek, and this time also with New Buildings Institute, is think about design, technology, and behavior. Create daylit buildings that maximize daylighting performance in existing buildings. Use integrated electric lighting controls and design to appropriately balance or complement the daylight, and then provide and think through the ways that users interact or engage with those things. And again, think about that from an annual daylighting perspective. Think about things like blind use and how those can start to inform and impact overall design. So first, before I get to Daylight Pattern Guide plus Energy, I'm going to hit the Daylight Pattern Guide, which is this tool. If you haven't used it before, I encourage you to. It's a free tool, again, with UW and NBI. What we did was took about a dozen or so different buildings from around the U.S. that we thought were exemplary daylit buildings for one reason or another, and we went through that process of post-occupancy evaluation and really analyzing them. So NBBJ's office is in New York, IDEA's office building in San Jose, Genzyme building, just to name a few. And we went and did high dynamic range photography, so we get, again, per pixel lighting from the real scene, and we did radiance modeling to match it through that calibrated process I illustrated earlier, show here. And then sort of backed it off to the point where it fails from a daylighting standpoint, and then if there was room for improvement, maybe suggested some additional ideas. So I'll just show you one example. There are 12 buildings and 19 different daylighting lessons learned. This is just the anatomy of one of those 19 patterns. Talks a little bit of a film strip, a little narrative about the building, photograph of the real building, and then the as-designed condition. So we recreate that in simulation, and then we use iterative design analysis to sort of take skylights away, add windows, take overhangs off, change interior surface reflectance, et cetera, et cetera. So this is an example that we see all the time of a really beautiful, well-daylit space, and then the occupants move in. Doggone it. This is what happens. Not that this would accumulate over time necessarily, but just gives you a sense of the nature of the tool. You can really screw up a well-daylit space if you bring the wrong office partitions in, right? And this is a problem that we had seen over and over again, and so we thought, well, let's just get this one done and make it so that we can really quickly illustrate this about why, if you want to do a well-daylit space, having 62-inch partitions is a real bad idea. There's a lot of metrics here I can explain. The floor plan on the far right and the 30% figure, that's the percentage of that floor plan that's above a lighting criteria. In this case, we picked 300 lux, or roughly 30-foot candles, measured horizontally on the work plane. And you can see how that number shifts as you go through these different iterations. The open office plate is about 90%, if I remember right, or 75%. And then, of course, it doesn't change as you add low desks or low desk with privacy screen, and it starts to drop as soon as you add partitions. The image on the top is that per pixel brightness, so that's the false color image representing each pixel as a luminance value. So again, 18 other lessons like this. And what we want to do is add energy metrics to it, because this is great from a qualitative standpoint, but that decision also has an annualized daylighting ramification, and that annualized daylighting has a resultant annualized energy implication, as we started to indicate, and layer in blind movement, et cetera. So what we want to do is take a few of these lessons that are the most common and bring it to a zone-by-zone level energy analysis or an annual energy analysis. That's currently a project we're looking for resources for. And we also want to start to get into visual comfort. A lot of the analysis in the current daylight pattern guide about visual comfort is a little bit more anecdotal. Certainly has some perception and kind of habitual methods baked into it, but we want to get to more rigorous, videos of false color maps and things like that. We think that could be useful. From a more functional lighting control layout, this would be kind of cool. This is just one static window-to-wall ratio, but looking at different lighting control zones. It's a little small. I apologize for that. But the red dots indicate a photocell, so a sensor to measure how much daylight is available and then dim the electric lights accordingly. And the black dashed lines suggest whether we're going to control just those or individual control zones or a bigger control zone. So here's your, no control, your perimeter on a photocell there, two separate zonal controls with two photocells, one control zone with a photocell, kind of the worst case scenario at the back of the room, et cetera, et cetera. And this shows the potential lighting energy savings from those different control strategies. And you can see it matters. So there's qualitative implications to those control decisions, but there's also measurable energy implications. Take that to the next level and think about sensor location by orientation and by period of the day. So you can imagine being able to slide a photocell around in that room and look at the resultant profile of energy by facade, or profile of lighting control by facade. And then thinking about window to wall ratios, there's one of the case studies looks at 10, 20, 30, 40, like that energy graph I showed at the beginning. It shows different window to wall ratios and what those implications are with sort of standard rule of thumb lighting control zone. So one standard rule of thumb is one window head height away is one lighting control zone. 2 window head heights away would be a second. And here are the little dashed lines that just show how those lighting control zones shift as you have more or less glass in your facade. So practically speaking, you probably don't get to control this second row of lights unless you're pushing at least to this 50% window to wall ratio, or you might think about trying to cheat those lights into the daylight zone a little bit and provide some supplement tax light or something. Impact of blinds, like I've already mentioned, is something that we want to look at. Here's another interesting one, just the impact of the different lighting controls, whether it's a full dimming, more of a step dimming, a step switching, and of course with LED we can even get the savings down to that nearly 0%. That would be another profile. Whereas with fluorescent we know we're kind of bottoming out at 10 or 20% power. Looking at those things by multiple climates, etc. So this one's kind of fun. A little bit of eye candy here, hopefully. This is a video, if it plays. Let's try it one more time. There we go. Okay. All right, I'm in full screen mode on one video while trying to run another one. How's that going to work? There we go. So this is looking at the impact of shading and occupancy hours. And most of the daylight pattern guide so far has not had electric lighting built in, so we've built the electric lighting in, and then we're dimming it accordingly based on a photocell control zone like I talked about, and looking at what happens to the total lighting at an hourly basis, lighting power draw on an hourly basis, and again how blinds would be implicated based upon different control strategies. So what you saw at the beginning was that this was before occupied hours, and so blinds were, with this control strategy, were open, and then as we came to occupied hours, hopefully it says something like 8 a.m. somewhere on this thing, that the blinds close and we're getting a little bit of dappled light coming through, but not nearly as much. This would be like a perf roller blind, up versus down, and then you can see the lighting power density change over the course of the day. So we're trying to find ways to illustrate these nuanced and somewhat complicated points more quickly to make them more effective in the design process. All right, almost there. Finally, just wrap up on a couple of the most bleeding edge metrics. A lot of daylight is moving more toward annual cloud files, where you have it's called a typical meteorological year weather file with real approximate. I say approximate. Typical, I guess, typical sky files. So looking at different cloud cover conditions and a whole range of different metrics. Just because we're running a little short on time, I'll have to hit this quicker than I want to. But let me just draw your attention to two metrics here. One is called daylight factor, and the other is called daylight autonomy. So what we're looking at is these different sky conditions or different variables that are important to daylighting performance, like can that metric consider solar disk position? Can that metric consider multiple sky conditions with regards to cloudy skies, sunny skies, variable time sequence skies? Is there an upper limit which says if you get too much daylight, it's bad? Does that metric consider blinds operation? And really, a couple of things to know is daylight factor is a really great metric for cloudy sky conditions. Just so happens that pretty much every climate has some cloudy sky conditions, so it's a good rule of thumb. Daylight factor of 2, which is to say 2% of the outside daylight getting into your space on average is a good starting or working goal. And then you have to balance it with solar disk analysis because daylight factor doesn't apply to solar disks. Whereas daylight autonomy, again, talking about these annual cloud files, daylight autonomy is intentionally built based upon annual conditions. So you need to run a simulation of, well, not quite 8,000 hours because it's night half the time roughly, but 4,000, 5,000 hours where you're doing that analysis and then adding it up and saying, okay, this grid point is above 300 lux 50% of the time on an annual basis, something like that. And then you sum that up across the whole room and you get a sense for how the room is performing. And then you have to decide, are you going to operate blinds or not operate blinds, et cetera, et cetera. So that's the world we're heading to. For what it's worth, that's the world LEED is heading to for its daylighting credit. But these are a little bit complicated to get your head around sometimes. So I tried to build two examples, contrasting examples. One is the Aon Center, which is your big monolithic downtown core high-rise, similar to the shape of the World Trade Center towers. And then you have Alliance Chi, a hospital in Northern Europe, much more articulated in form. And you can look at a single point in time. Let's say, what does it look like on September 21st at noon on a cloudy day? And you can see that 33% of the Aon building is above 300 lux, whereas 89% of the Alliance Chi building is above 300 lux at a single point in time. Does that make sense? So then, how does that perform all of these different metrics? Again, I'll just draw your attention to daylight autonomy. Where did it go? Right here. So this build is it dead? Battery died. All right, I won't back up. We're almost there anyway. So kind of taking that idea forward of daylight autonomy as one of these metrics that we're going to be dealing with in the future of daylight analysis. I'll just remind you of the energy graph I showed earlier. This is what is behind that graph from a lighting standpoint. And what we're doing is, this is the daylight autonomy plot, where 0% in this case with 10% window to wall ratio, 0% of that space, it's all black, is above 300 lux for half the time. So none of that space is above 300 lux for half of the year from 8 a.m. to 6 p.m. And as you ramp up to 20% window to wall ratio, you can see how that improves. And as the colors get lighter, the scale is a little small there. I apologize, but the orange line is 50%. The black line, the black dotted line is 70%. So as you would imagine, more of the room, or less of the room is above 300 lux for 70% of the time, and a little more of the room is above 300 lux for 50% of the time because it's less time. And then what it looks like at 40% window to wall ratio, and 50%, and 60, and 70. And of course, I've already said that's great, but that's not enough because that's assuming blinds are up all the time. So this next metric takes that number, takes that concept of daylight autonomy, sums it to a single number for a room, and makes the blinds do all sorts of crazy things based upon the annual solar disk analysis. So again, photograph on the top, rendering on the bottom. Annual metrics for this classroom. This is Ash Creek, Bora Architects, one of my favorite school buildings. You can see it's got pretty decent for perimeter to core depth, about 32 feet deep. I've lost my pointer. About 32 feet deep. We've got an overhang and a light shelf, and we have a relight at the back of the room, and we also have a solar tube there. Now, what happens here is without the overhang and light shelf, which is what you're seeing here, and without the solar tube, I'll also add, because we were doing this when we couldn't quite get the photometric file to work right, and that was our fault. But So without the solar tube and without the exterior overhang and interior light shelf, we're seeing the daylight autonomy number. And we're putting it into a spatial number, so it's one number to sum that whole room up, and it says it's 28%. And we're also looking at, the annual sunlight exposure number. And that is to say, the portion of the room that sees more than 250 hours of direct sun, assuming the blinds are not operated. So that's what we have here. And we see 30% of the room is above has more than 250 hours of direct sun, and 28% of the room is above 300 lux for 50% of the time with the blinds operated and no exterior overhang or interior light shelf. So when we add the exterior overhang, darn it, there we go. When we add the exterior overhang, hopefully, come on, there we go. All of a sudden, the daylight autonomy number jumps way up to about 55%. And that's because the blinds have to operate way less often if you have an exterior overhang and interior light shelf. And so you're getting that benefit of doing those architectural design decisions. And lo and behold, the annual sunlight exposure drops to 10%. So the goal that IES has recommended is to use these two metrics, to use spatial daylight autonomy to guide your design decisions, and use annual sunlight exposure to check them. And see, the goal is to lower the annual sunlight exposure number and increase the spatial daylight autonomy number. And that's just one quick lesson learned, one quick case study example of how those metrics work. Not very many software programs have those baked into them yet. So Diva for Rhino has apparently done it, though I've not used it. And we have a Radiance script, which I promise you most of you are not going to want to try to do, but eventually the software programs will be baking these metrics in. It's one thing for a space, and then it's all that much more complicated to look at a whole floor plate with these metrics. And really, the state of the science right now for using these metrics is more at a space-by-space level. I would venture to say we're one of a few that are trying to look at how these metrics apply to a whole building. But here is the spatial daylight autonomy number for a whole building. It shows it at 78, and this is with the blinds operated using the correct trigger. And then here is what the annual sunlight exposure number is, and I didn't sum it. I apologize, so I can't guess to what it really is, but you can see the layout there, and 250 hours is the red. Anything that's actually getting cut off those edges is above 250 hours. All right. Just want to say thank you to Alan and Amir in particular for a lot of their research work and helping to put this together. Time for questions and a brief announcement. Baby Dominic was born 2 weeks ago, so thought I'd share that little photo with you and ask for questions. And we can turn lights on or whatever. Everyone was telling me, no way you get through 152 slides in 90 minutes, but it worked. Should we try it?
I think that one works out. Questions for Kevin?
My question is, when you talk about all the warm and cool light, especially, what does paint color on the walls and the floor have? How do they affect that? And
it absolutely does affect it. All things being equal, the white wall, 3,000 Kelvin will seem warmer than 5,000 Kelvin. There's a lot of complexity to the answer really to that, because our eye also can accommodate some of this variability. You go into a room with white walls and 3,000 Kelvin lamps and the walls feel white to you. You go into a room with white walls and 5,000 Kelvin lamps and the walls feel white to you. They might feel a little bit cooler white. It might feel a little warmer white in the 3,000, but it still feels white. So our eyes can sort of accommodate or adapt for some of that. But so your question about paint color is absolutely relevant as well. And it's just another layer. It's another tool, that, another interacting effect that you need to consider as you're thinking about color temperature lights as well. So you can put 5,000 Kelvin lamps on a wall with a paint hue of, you know, a tinted yellow, and it will start to pull it to feel a little warmer. But you know, that's a little beyond. That's about as far as I can go with a answer that I feel confident in. I think experimenting would be the way to do that. So color boxes, light boxes, so you can create some white light boxes and just put different lamps in them, lamp types in them, and then put different color or paint on the inside of those light boxes. Seattle Lighting Design Lab is a great place to have that all set up if you happen to go there. But it's something that you could do at a reasonably low cost budget for an experiment.
Any more questions? Gunnar has one.
Got it. So
Gunnar's trying to get that book.
So I don't know if you maybe have seen it. There was an article in High Performance Building magazine called Rethinking Daylight.
I have seen it, and I've really quickly skimmed it. But yeah, go ahead and summarize it.
So the gist of the article was with the highly efficient LED lights, the extreme low power densities, and in their case, they were doing net zero.
Right.
The lowering costs of solar panels.
Right.
They had downgraded. They came back to their project after the fact. They had kind of done some of the same things that we saw there. They came back to it and said, well, if we did it again using LEDs, we might do it using the LEDs, add a couple more solar panels, take out some of the daylighting windows in the classroom, and we're saving more capital costs at that time. So the question that I had was, what are the top 3 things that would you say to combat the going towards the technology route, I guess?
Right. So the argument there is that solar panels are dropping in cost, LED are getting more and more effective lumen per watt, and their cost is coming down. We don't need daylight anymore, basically, right? It's a liability. We'd rather just we don't want to put a skylight in, we want to put a solar panel in. And my immediate answer is, why use energy to then have to put a solar panel in to buy more energy? There's still embodied energy in all of the pieces of equipment that you're buying. So that's the sort of energy-specific answer. Maybe the more important answer is the human factors answer, and that is, we're designing places for people, not to save energy, right? And if you're optimizing on the economics or optimizing on the energy, maybe that's the right answer, but I still don't believe it if you think about it, total embodied energy. But I think if you're optimizing on the human, it's not the right answer. I think we would rather see the variability, the connection to the weather, the connection to the outdoor information and view, and those have benefits that far outpace energy.
Well, I think we're just about there on time. Any other burning questions in the last 2 minutes? Going once, going twice. All right. Thank you. And that was very great.